Hello and welcome to our first session on trigonometry. We are going to take our time just introducing some key concepts and then slowly build on that to where we can have some interesting problems with some practicality to them at least. But many, this topic, if you haven't really heard of this before or really um, come across this, then it can be a little tricky. We are going to take as informal an approach as we can, but uh, the topic to a large degree is quite mathy, right? So we'll try and keep things in check and see how we go. I'm going to take the approach here of just revealing um, content as we go because I already happen to have it written up, but hopefully it's not strange. Too many new things at once on the screen. So we're introducing trigonometry. And trigonometry is the study or use of angles. Talk about an angle. Well, when you ask a random person about angles and how you measure them, or you ask them for an example of an angle, they're going to give you something like 30 degrees. There it is. I can visualize that. I have a sense, based on my life experience, of how wide, so to speak, 30 degrees is. How wide, how big is that angle? So, talking in degrees is nice and presentable, intuitive, and natural feeling way to refer to an angle. But what is a degree? What are you really saying? Is a degree? What does that mean? Well, long ago, people that developed these concepts decided, well, if we look at a full circle, we're going to break that full rotation up into 360 smaller pieces, equal pieces. Why 360? No one really knows. These kinds of numbers in history were often taken to be the most convenient, like multiples of 60, 24. We see it in our calendar, in our time, measuring in 60 seconds in a minute. 24 hours in a day. Those numbers were deemed at that time in history to be convenient because they had a lot of uh, divisors that people could work with. They could be split up into a lot of different pieces. Uh, and we still sort of have that today. 360 is one of those. So we split up this full rotation into 360 equal pieces. That is essentially our unit degree, the unit with which we measure angles. But it is a unit of measurement. It's a unit of angle measurement. So when I then have an angle like 30 degrees, what does that really mean? Well, it means the same thing it did for length measurement, for area measurement. I'm seeing how many of this unit area wedges I can stack in to fill this given wedge angle. And I can stack my little unit 30 times in here. Therefore, this angle is 30 times bigger than the unit. And we say it's 30 degrees. The concept of measurement is the same, but we're dealing with a different thing, for lack of a better word. We're working with an angle and not a length or area measurement as you may be used to. So they needed to come up with a new unit to uh, make sense of different sized angles. And the degree unit felt at that time to be a perfectly good one. right? Right. There are pros and cons here. It's certainly intuitive, but mainly because I've grown up with it. I've been exposed to the word degree and the concept of an angle slowly through school and just life. So it feels natural because of the time I have spent with this concept, hearing it, thinking about it, talking about it. It feels pretty good. But it turns out in this mathematical world and language, when things get a little fancier, the degree measure, the degree unit is not the ideal thing to work with. I can compare this, not quite, it's not quite the same, but I can compare it to, in a way, to percentages, where when I when I talk about uh, ratios and proportions and things like that, I might talk in percentages. It's an easy way to convey information. People understand it. But when I work with calculations, especially fancy calculations, more complicated calculations, percentage isn't in a calculation. A percentage is a way to present the information at the end or the beginning, not in the calculation phase. I would use the decimal equivalents of those percentages. So it depends on my use. If I'm just casually talking about angles, degrees are perfectly fine, no problem at all. And it's difficult for us to understand at this level. I totally get it because you don't know those fancier situations. Why would degrees possibly not be effective? Trust me, they're there. When you talk about functions and you're mixing different kinds of quantities, they can't have units because it doesn't always make sense. The question that I'm asking, the sentence that I'm saying doesn't always make sense. For example, I could say 2 apples plus 2 oranges equals 5. Well, 5 what? You say, well, fruit. Sure. So I've had to modify the units here to make a new one, and maybe it works sometimes. But it was a very simple calculation, a very simple sentence mathematically that I wanted to say, though these aren't actual units. However, there are many other units, right? If for some reason I need to somehow combine, even if it's more complicated than I'm showing here, I need to combine a length and an angle together. Do I, does it make sense to say 7 kilometers plus 30 degrees equals 37? Makes no sense whatsoever, right? So in general, when I have units, especially different units, attached to quantities in a calculation, well, the answer doesn't always make sense. I can't have those units be attached to and different units in the same calculation. It just doesn't work for very long unless I say very, very simple things, of course. So people realize this because they're not going to just add a couple of apples and a couple of oranges for very long. They had calculations to make, they had buildings to build, and very important things. So we need to relate the angle concept to a length measurement. Length is established, we understand it, we can flip back and forth between units, we can standardize it, all good things. Now the angle concept comes in and it wants to play. We need to work with it. When building a building, yes, there are the height of the building and the length of the material and whatever. Angles are always there. We need to somehow merge these things. so that they don't conflict with each other in calculations. And one way to see it is relating an angle to a length concept. Not a specific unit, just a concept. Well, let's think about this. Let's think about it. If I make a circle and a little wedge that has the same angle, let's call the angle theta, the Greek letter theta, often used for angle names. It's the same angle, but this left circle is smaller than the right circle. So if I now look at the arc here that spans that angle in the first circle, I'm traveling along this arc. There I go. I'm traveling. I didn't travel that far. But the distance that I travel is related to the angle. No doubt about that. If I make the angle bigger, I'm going to travel a longer distance along the circle, for sure. But now I'm keeping the angle the same. My circle is bigger. Even though the angle is the same, I'm traveling a longer distance. This S2 length, this arc, it's longer than the arc S1, even though the angle is the same. Because I've expanded the circle and the radius R2 is also bigger than radius R1. So it's not quite as simple, but there's certainly a link between the angle and these other length measurements. The arc that it spans it, as well as the radius of the circle that I'm walking on. These three things have a relationship. And with further investigation, it turns out, whoopsie, random line. It turns out that if I keep the angle the same, trying to relate an angle specifically, yes, those two, arc length and radius, they change because if I change the size of the circle. However, what's interesting is that the ratio of arc length to radius is always the same, regardless of the size circle that I work with, as long as the angle is the same. So even though an individual length doesn't directly correspond to an angle, this ratio does. So once people realize this, they say, well, we could refer to this angle not by degrees, but by this ratio, because this ratio is independent of the circle size, only dependent on the angle in this little wedge. The angle is the same. You can pick any circle you want. The ratio is going to be the same. Arc length to radius will always be the same. So we can refer to an angle by this by this ratio rather. That ratio is unique to that angle. Make the angle bigger, it'll have its own unique ratio. I keep saying the wrong word. It'll have its own unique ratio, arc length to radius. Light bulb moment. There's a different way, by way of this ratio, to refer to an angle. You can refer to it instead of the size in degrees, which is a little archaic when you think about it. At the time, they needed to come up with something, they came up with degrees. Why 360? It was just made up at that stage. This is a little bit more sophisticated. By understanding, we can refer to the size of an angle by way of this very unique ratio attached to it. They go hand in hand. An angle, specific ratio. Different angle, different ratio. But different angles won't share this ratio. It's 1-to-1. It's unique. So, if I just state this in general, I have three players in this relationship. Angle, theta. Arc length, s. Radius, r. I can, of course, shuffle these things around, depending on my needs, right? I can also say the arc length that spans an angle is the radius times that angle. Different uses, keep them both in mind, but this first one for now is sufficient. So I write an equal sign here, but it's really kind of relaxed. This is going to be my new measure. It's not really an equal sign. It's a correspondence. The angle uniquely corresponds to this ratio. And therefore, I can see that ratio as the label, the name, the size of that angle. So because I have a ratio of two length measurements, regardless of the unit, those units will cancel. And technically, it's even better. The angle measure that I've created here is unitless. It has no unit, which means I can apply it and move it around and put it with many things. Though understandably, I do have sympathy. You don't necessarily really know why it's so useful because that's way into the complicated future that we might never see, unfortunately. It doesn't have the same restrictions that the degree measure has in terms of how I can use it in calculations. We're going to call it the radian measure of an angle. Different. Think of it like, it's not quite a good analogy, but it's the best one I have so far. Think of the English system. Feet and yards. Why is there 1,760 yards in a mile? If you didn't grow up in that system, it seems incredibly inefficient to have those units. Why? Because historically they were systematically developed. They were developed all at once with future proofing in mind. However, if you grow up with miles and yards and feet, it's perfectly fine. You're used to it. No problem at all. Though, when you sort of zoom out and think about how efficient things can be, yards and feet and those conversions aren't really the best option, right? Which is why we standardized it to the international system, which most people use for its efficiency. Similar things are happening here. Degree, the degree measure of an angle, talking about an angle in degrees, great. If I'm just talking, no problem. And I grew up with it. I have a good picture in my mind for how big 45 degrees angle is, a 30-degree angle, a 60-degree angle, a 90-degree angle. Those are uh, those feel natural to me because I grew up with them. And for talking, no problem. But for fancier things, not as efficient. Not as efficient. The radian measure is sort of my international standard for measuring and talking about an angle and using the angle size as in a calculation. We're going to call it the radian measure. But it doesn't quite make sense yet, does it? It's great. Sounds wonderful. Okay, good. But if I think about an angle like 30 degrees, what is that in radians? What's the corresponding measure? Just like if I think about yards or miles or feet, it's great. I have a better unit system, but what is that in meters? I need to be able to convert it. That's the important thing. Luckily, when these things were first thought of, the Greeks understood that this was very important and they came to the rescue and figured it all out for us. Those Greeks. So let me just display this systematically here. Lost my ability to move stuff. That's always a very nice. There we go, it's back. Very nice glitch. So let's look at a full circle. Full circle, full rotation, all the way around. There is an angle involved here, of course. The 360-degree angle. Just a full rotation all the way around. It doesn't really look like a wedge that I'm traveling along. I admit it. However, it is there, right? There is an arc length here. It's just a full circle, the circumference of the circle. So I'm not going to use an S because the circumference sort of has its own letter, C, but it's the same role as that arc length. So I know that the 360-degree angle here that the circumference spans is related to the ratio that I travel around on the circle divided by the radius, r. Remember, theta, s over r. It's the same thing, just making it full to a full circle. So the Greeks went and measured many a circle. To compare, at that time, they wanted to compare the diameter, which is just double the radius, cutting the circle in half from end to end, or from the circle to the other side. So double the radius. They wanted to look at the diameter. It's done. Can't stop it. And compare that to the circumference. So they measured many circles, a small circle, a large circle, a medium circle, a tiny circle, all kinds of circles. Measuring how the diameter compares to the circumference of the circle. And they found, to their amazement, and really it is arguably the most important discovery, arguably, that the ratio of circumference to diameter is always exactly the same. Now, they might not have been able to calculate this many digits, but now we can calculate on as many digits as we want almost. And this ratio is a weird decimal number, 3.14159, and it never ends. I just wrote this on from memory, so I apologize if a digit is wrong, but they call it pi, another Greek letter. It's a non-terminating, never stops, non-repeating decimal. It never has a pattern that repeats again. And it comes from such a simple geometric shape. The circle. You look in the sky, you see the moon, you think of circle. It's not a perfect circle, I know, but you think circle. An object, it's a shape that appears in nature. Yet it's weird, this weird number that never ends, never, never repeats. It's fundamentally attached to this simple geometric shape. That's weird, but it's true. The ratio of circumference to diameter is always the same regardless of which circle you look at. It is a constant pi. Okay, great. Great discovery. How does that help me? Because remember, my question was still, you claim that there's this better, more effective unit of measuring angles than compared to degrees. So how do I now convert into that unit? How does pi fit into anything? Mhm. Well, let's reveal this systematically. So this is their discovery. They call it pi. It's forever in the record books, the history books rather. It is equivalent, or it is equal to the ratio circumference over diameter. Now, diameter, I'd rather talk about radius. So I'll simply replace the diameter with 2 times the radius, which is exactly what it is. Then I'll multiply both sides by 2, because I don't like that 2. So the ratio of circumference to radius is 2 times this constant pi. But wait a minute. In degrees, I know what the circumference to the radius ratio is. It corresponds to 360 degrees. Therefore, 2 pi corresponds to 360 degrees. It's a correspondence. You can say equal there, and we do. Technically, it's not. It's just a correspondence of units. Or, I like to remember this one. If 2 pi corresponds to 360 degrees, then pi corresponds to 180 degrees. There is my reference pair, my conversion pair. Just like I would have to find, which one did we use? We use centimeters to inches or miles to kilometers. I need a reference pair to link these two units. Here it is. That 180 degrees is equivalent to pi radians. Yeah, interesting. Let's not say it ugly. It's not ugly. Interesting decimal number. Certainly is interesting. That's my reference pair. Bank it, memorize it, it's done. So then the only thing that is really left is using it. Just like when we converted length units, practice that a little bit. Same thing now. I want to just practice converting between these two units for measuring an angle. So let's go to our book. Let's zoom it in. There we go. And we want to convert between degrees and radians for these. So you see here, some are in degrees, and I want to convert to radians. Some are in radians, I want to convert to degrees. I will need to go back and forth, just like I did for length measurements. The concept is going to be the same. What was that concept? I don't see everything. Hide it. What was that concept? Well, I have a reference pair, and it's even better news in this case, because in this case, I have one reference pair. There is nothing else. That's the only one I need. 180 degrees correspond to pi radians. Now we say radians, though it's just for show. It actually doesn't have a unit, but you can think of it as a unit to keep track of it. So 60 degrees, that's our first one, right? 60 degrees. I then have to multiply by my reference pair and just position these things in the correct way so that the degree unit cancels. Now it's not necessarily a letter here, it's a little circle at the top. The degree unit cancels, and I'm left with radians. 60 times pi over 180, and I get the decimal number. That's actually, of course, non-terminating. I have to round it. 1.0472. Meh. It's rounded. It's not very precise, and it's not very pretty. The alternative that I prefer, and that is always preferred, is to keep it sort of exact, which means I don't use a calculator. I don't calculate pi in this calculation. Oh, I don't use the decimal version of pi in this calculation. I keep it in symbolic form. So 60 at the top, of course, that's over 1, right? 60 times pi over 180. And then I simplify the 60 and the 180 to 1 over 3, and my exact answer is pi over 3. Now it seems a little strange in the beginning if you haven't seen it, but like anything, you see this enough times, you repeat it enough times, it becomes second nature, really. Really. It does make sense when you think about it a little bit, in that 60 degrees is a third of 180. So the corresponding radian measure should be a third of pi, which it is, pi over 3. So please take care. The question says without using a calculator, you have to find the exact value. You do it this way, not the top way. Next one, 30 degrees. 30 degrees, same thing. Multiply by my reference pair so that the degrees cancel. 180 degrees have to be at the bottom. 30 over 80, pi at the top. Looking for the exact one, simplify the fraction 30 over 180, I get 1 over 6, pi over 6, which makes sense because 30 degrees is 1/6 of 180, so the corresponding radian measure should be 1/6 of pi, pi over 6. Just takes time. When you're seeing this for the first time, it just takes time, like anything. In number 3, I have pi over 4 radians to degrees. Pi over 4 radians to degrees. So pi over 4 radians times the reference pair. Radians will now go in the bottom to cancel the radian quote-unquote unit, which I can think of as a unit, to keep track of it. And degrees stay at the top. The pi's cancel. 4 is at the bottom, the 180 at the top. 180 divided by 4 is 45 degrees. You can also think of it, well, pi over 4 means a quarter of pi. So a quarter of 180 degrees, 45 degrees. So these angles, these are common angles we'll see many, many times. And after a while, you just memorize what they are. But I can think of it in terms of fractions of 180, and therefore corresponding fractions of pi. Next one, 5 pi over 4. Now, as these angles, regardless of the measure, become a little bigger, people start to struggle. But the method that I use does not change. I have my given angle in radian measures here, 5 pi over 4. I need to convert it. It's the same reference pair. Position the radians at the bottom because that's the given unit. Degrees at the top. Now simplify. The pi and the pi cancel. I have 5 times 180 at the top. I have 4 in the bottom. Simplify fraction, or try a calculator at this stage, it's fine. 225 degrees. What's even a little bit more tricky for people is going from a large degree size to radians. Like, for example, 270 degrees. But it doesn't change. The method doesn't change. Multiply by a reference pair. Now degrees go in the bottom and radians at the top. Put it in fraction form. 270 over 180. I can simplify that systematically. Maybe 27 over 18 by dividing by 10 both. Let's just erase the little line here. 7 is attached to the pi. And then maybe I divide both sides by 9 to eventually get 3 pi over 2. So it has to be in simplest form. Simplify the fraction, but leave it exact. So these are a little bit less common and therefore a little bit more difficult. You get used to them slower, but the method does not change. It just takes practice. So all we're doing in this session is getting used to this new angle measurement unit, radians. There are some to practice here in the problems. Of course, there are other things in the chapter. There are more sessions. Don't worry about the functions right now. We'll get to them soon enough. Problem 15.1. I have some angles in degrees. Just convert them, just like we just did. Problem 15.2, I have some radian measures. Convert them, just as we did. Don't worry about the rest. We still have to talk about them. But there is some stuff to practice. Figure out what are you comfortable with? What are you not comfortable with? Focus in on that and start getting comfortable. It's just a matter of repetition. It's just a matter of time. Right. We will pause here so that you can go practice and pick it up next time. Until then.